how are people feeling about last class? We introduced the calculus of variations. I think for most people this is new. It's an entirely different way, as we saw, an entirely different way to arrive at the equations of classical mechanics, arrive at Newton's laws. Instead of kind of writing these things down, it's a way to use ideas about energy to derive the laws of motion. And we looked at it, there's kind of two basic frameworks for doing variational calculus. And we're going to primarily focus on one of the two for this. So there's two approaches. These are things you've heard before, most likely in a dynamics course. But there's the kind of Lagrangian mechanics. I'm not sharing. Oh, thank you. Hold on, let me share my screen. I'm not even on Zoom. I am all off this morning. All right. Holmes iPad, there we go. Let's see here.
Looks like there's a question.
Yeah. Go away. There we go. Okay, cool. All right. We introduced the calculus of variations last class, and we did it from the framework, kind of one of two equivalent frameworks that allow you to arrive at the equations of classical mechanics. The one we did was by minimizing what's referred to as the Lagrangian. The Lagrangian has this fancy L, and it's equal to the difference between kinetic and potential energy. Another equivalent framework to study these problems, arrive at the equations of classical mechanics, use variational principles to do so, is what's referred to as the Hamiltonian. And the Hamiltonian is the total energy in the system, so it's adding up the kinetic and the potential energy. For the sake of time, and since this isn't a course entirely devoted to variational calculus, we end up focusing all of our efforts on Lagrangian mechanics. But these same principles apply, that you end up with a different form of the energy. In the Hamiltonians, you're typically thinking about kind of a set of generalized coordinates, and you're thinking about momentum. And the end result is you end up with kind of more first order equations with the Hamiltonian system. And in the Lagrangian system, you end up with fewer equations, but they're of higher order derivatives. So there are times when for your given problem, it might be easier or harder to solve them based on how complex your equations are. Those are kind of the simple basic differences, but a lot of the approaches that we're using can be mapped between the two of them. So we're looking at the calculus of variations, where we define a Lagrangian, some kinetic energy minus potential energy. We minimize the functional, and we arrive at the differential equations that we want to solve. And that's exactly what we did last class. We wrote down the kinetic energy for a ball being thrown up in the air. We wrote down the potential energy, just kind of generically as just V. We went through this complicated process of introducing a perturbation to those states. We then went through and said, well, that perturbation is arbitrary and it's small, and if we have the actual true curve, we should be able to take that perturbation to 0 And what we ended up with is finding that there's some equation, which turned out to be F equals MA, that is the minimizer for the total, for the Lagrangian in that system. I kind of wanted to start to see what questions you have about this process, about last class. What we did was derive a really familiar equation. And what we're going to do today is also derive a really familiar equation, but doing so in kind of in more general than working on a specific problem that led to Newton's second law. Before that, I want to introduce to you what's referred to as the Gateau derivative, which is something we were doing. Actually, we've been doing this for the last several weeks. I just haven't explicitly told you that we're doing this. And I think when I introduce it to you and then show you what I mean, you'll kind of see the connection. And so to calculate the first variation, we can so the first variation in general we recall that we had introduced y and eta, and these are functions. And then we had introduced epsilon, which is a scalar. Draw also vectors as well. And this thing is usually very, very small, consistent with everything we've done so far. The first variation takes on a very formal definition that can be intimidating at first, but we'll break it down. And the first variation looks like this. It says the first variation in S, which is a function of y, eta, is equal to the limit as our small parameter goes to 0 of our perturbed action taking away the true action, the one that we're interested in solving, divided by epsilon. This seems perhaps a little intimidating, but it gets a bit simpler because what we're really doing here, and this is actually true to some of the ways that we started talking about kind of confirming whether something was an asymptotic expansion or not, looking at the difference between the function at each order of epsilon. So really, we can kind of look at this in a different way where we say we can take the derivative of S bar with respect to epsilon, and then evaluate that derivative at epsilon is equal to 0. You might see this written in a different way, in which we write d S bar, d epsilon, at epsilon equals 0. Equal to 0. This is what's referred to, don't want that. I want to write. So this is what's referred to as the Gateau derivative. GA with a little hat. Those of you well versed in calculus might recognize this as equivalent to the directional derivative as well. This is kind of giving us a recipe. This is how I like to think about it. We take our action. Our action is equal to the integral of the Lagrangian. So remember that, what is S? So what is S prime? So S is equal to the integral from T1 to T2 of the Lagrangian over time. So we take our action. Our Lagrangian we know is going to have, at the simplest case, one dimension of, say, space that we're interested in this case, like the ball going, the height of the ball. And we perturb the height of the ball by adding a small function to it. We know that epsilon's small, we don't know anything about eta, we just know that eta is arbitrary, and we're just going to add some small arbitrary function to the actual solution. And the Guiteau derivative gives us a recipe. The Guiteau derivative says, okay, you've taken your action, we're going to call the action that we've perturbed S bar, because we've taken the action which is a function of y, and made it a function of y plus some small perturbed function epsilon times eta. We're going to take that action, we're going to take the derivative of that action with respect to epsilon. And then after we take that derivative, we're going to replace epsilon with 0. And the resulting equation is our first variation. We take the action, we perturb it, differentiate with respect to epsilon, we set epsilon equals 0, we have the first variation. When the first variation is set equal to 0, that is what's called a stationary point, an equilibrium point. We have found an equilibrium solution to our system. We don't know whether that equilibrium solution is a minimum or a maximum. There's extra work you can do to check that. But we found a stationary point. We found the point that either minimizes or maximizes the action.
Is that extremal of the perturbed system or an extrema of the system as a whole?
So the question was, is that solution the extrema of the entire system or the perturbed system? And it's an extrema of the actual system. And the way you can connect that to the perturbed system is you can say, once you've found S, if you perturb that, you're guaranteed to have an action that's higher, because the principle of least action tells us the system is going to follow the lowest value of S, which is just a number. And so anything else where you take that and you perturb it by adding a small parameter times a function, is going to give you a higher action. So this is the extremum of the actual true system. The perturbation is just kind of like a detour we take to help us find the right equations that minimize it. Let me see if I want to do this. Let's go back to the projectile problem just for a second to help translate this into something useful. So let's go back to the projectile problem, and let's do this over here. So, and what I'm going to do is write down stuff that's already in your notes. So you should be able to flip back. You don't have to do it right now, but this is stuff that we've done before when we perturbed the projectile problem. Okay, so when we perturbed the projectile problem, what we said is that f of x is equal to x naught double dot plus epsilon x1 double dot plus epsilon squared x2 double dot. And that was all equal to -1. You remember this is the gravity term. And then we had some additional terms coming from the nonlinearity of the system. So we had 2 plus epsilon x naught minus 3 epsilon squared x1 squared. If if we want to look at the first variation of this Gotow derivative helps us in the exact same way as it does for the more complicated form where we have an action. Here we have a function. The Gotow derivative allows us to calculate the first variation. We have a function O, but it works just the same here. So we can say, okay, I would like to follow the steps that were just outlined to me. I perturb my function, so I add this epsilon term to it. So I've already done that. I've expanded everything and added a solution that took x instead of equal to x naught plus epsilon x1 plus epsilon squared x2, and then all the subsequent derivatives as well. So the Gotow derivative says, okay, once you've perturbed your function, take the derivative of it with respect to epsilon, and then set epsilon equal to 0, and then you have the first variation. So we can come over here, we can say, okay, well, what is df d epsilon? Well, that's pretty easy. The first term goes away. The second term just becomes x1 double dot plus 2 epsilon x2 double dot plus other terms equals what's happening here. The first term goes away. We're left with 2 x naught, and then minus 6 epsilon x1 squared. Is that squared? I think it's squared. Yeah. Plus other terms. And now the Gotow derivative says, okay, once you've taken that derivative with respect to epsilon, evaluate that derivative at epsilon is equal to 0. Which just becomes x double dot, x1 double dot is equal to 2 x0. And you'll notice that the plus dot dot dots went away too, because every term that's in the plus dot dot dots has an epsilon to the n, and we've said take epsilon to 0. If you go back through your notes, I almost wonder if I should look, but I'm nervous to do so. What would it be? If you go back through your notes, what you'll find in the regular perturbation of an initial value problem is that, yes, okay, actually I'm gonna do this, hold on. So keep in mind that this is saying that the order epsilon solution here is that x1 double dot is equal to 2x naught. So let's go back, regular perturbation of an IVP. Here we go. The order epsilon solution of our ODE was x1 double dot is equal to 2x naught. If you want to calculate the second variation, attempted to start an invalid broadcast session. I don't know what that means. So this equation here, oh, whoa. Where did my thing go?
So it's stuck on the right stuff.
I lost the ability to use the mouse pointer. Okay, well, anyway. Hopefully you can see that the order epsilon solution here is exactly what we just solved by using the Gotow derivative. So we can find the first variation. So the first variation of our problem. Why is this thing? What is happening today? What is happening? Sorry, everyone. Oh, for crying out loud. Okay. There we go. I got my pointer back. Okay. So this quantity here at order epsilon is exactly the same as what we just solved using the Gotow derivative. So there's a connection between calculating this first variation. The use of epsilon as our small parameter in perturbations and the way we think about variational calculus are connected. And this is the kind of the reason why we started with these perturbation methods, to introduce you to the idea of perturbing a solution and adding a small parameter to it. And the way we did it in the perturbation methods for approximating, we were adding that small parameter as a way of kind of adding back in the nonlinearity bit by bit. And here what we're doing is we're adding a perturbation as a way to help us find what the true minimal solution actually is. And this Guiteau derivative is kind of the recipe for how we do that. So what do we do now? Well, what I'd like to do now is calculate the kind of maybe the most fundamental and basic functional that you can dream up. And this will result in an equation that I think will be familiar to most of you. And so we're going to do this same process as we did last class, but we're going to do it in general here. And we're going to say,
can I jump in with a quick question?
absolutely.
So looking back at when you defined the Guiteau derivative, I think I'm just a little confused with the notation, because here you're saying that S bar is the function of y plus epsilon eta, and S is the function of y. But I think last class, we were looking at S bar as just the function of y, and S is the function.
Did I flip those? Oh, yeah. Did I flip that last class? S was the true thing, and S bar was the, no, S bar, oh. Oh, yeah. S bar was the true thing, wasn't it? Sorry. So you're saying this, and then that means we did this. Yeah, thank you. Sorry, my notation was backwards for some reason. Thank you. Okay, so our goal is to be able to write down any arbitrary Lagrangian. Lagrangian is kinetic energy minus potential energy. That Lagrangian is going to take typically, say at a minimum, one independent variable, one dependent variable. So say something like space. So our independent variable would be maybe x or t, and our dependent variables might be like y. We also might consider dependent variables having derivatives. So we just like in the last problem, we looked at velocity. So it was the derivative of our location, so our dependent variable. So we can write down a generic functional where we can say, well, I want to consider the action S. This is going to be evaluated between two arbitrary points in space. And my Lagrangian, I'm not going to tell you anything about it. I'm just going to tell you that a Lagrangian is going to consist of an independent variable x, a dependent variable y, and a dependent variable y prime. In the last problem, this is like time, space, velocity. But this could be, for a beam, this could be x distance, deflection, slope, something like that. So you can kind of, whatever you want these things to be. What we're going to do is the same thing we did before, where we're going to say, okay, I would like to let us introduce a new variable. We'll call it y squiggle, y tilde, which is a function of x, which is going to be equal to our original y, which is a function of x, plus epsilon times eta, which is a function of x. We also know that in order for this to be useful to us at all, and we saw this in the last class, I'm just repeating what we already know, that eta here has to match exactly our y tilde function has to be exactly equal to y at the points x1 and x2, which means eta at x1 and x2 has to be 0. So we can say that eta at x1 is equal to eta at x2 is equal to 0. You might see this type of language written differently if you dig into this literature a bit more. And what you might see is that people introduce the first variation, delta y, which is equal to the difference between my perturbed y and the real y, which is equal to that quantity there, epsilon eta x. For the sake of these lecture notes today, I'm not going to use this notation. I'm just going to stick with what we did last class. But I want you to know, be aware that this is often how you'll encounter this, especially in mechanics textbooks. Like especially if you were doing like elasticity or anything with solid mechanics, where you're going to almost entirely see this kind of variation in deflection, variation in slope, variation in curvature. So this will be the notation that's familiar. It's just equivalent to the kind of the difference between your perturbed function and your real function. That's all it is. Okay. I think I have everything. So what did we say? The real one is S bar and the fake one is S. Is that right? So I'm going to change that here too. No, actually, oh, that's probably confusing. How do I want to do that? Did it all backwards, did I? Shoot. Okay. We'll do, you know what we'll do? We'll do it this way. Since we're doing a tilde here, we'll do our new stuff with a tilde. So we'll do that our perturbed function is going to have our little tilde on the S. And we're going to integrate between x1 and x2. And our new Lagrangian, our perturbed Lagrangian, is going to look just like x, y tilde, y prime tilde, dx. So I have to write dx up here. Which we can write out to make it more explicitly clear what we're talking about. We can say that our Lagrangian is going to be x, y plus eta, y prime plus epsilon eta prime dx. One of the things I want to note is that you always are perturbing the dependent variables. You're not perturbing the independent variables. So we haven't done anything to x. X remains the same. What we're doing is we're perturbing y. And we're saying, well, let's just add a little function to it. We don't know what any of this is. We're doing this completely in general. And so what we can do is exactly like what we've been doing up until this point. We can start expanding. And as I've said multiple times, take nothing else from this course, Taylor series expansions are your friend. So what we're going to do is we'll expand this in a Taylor series expansion. We'll say that S tilde is going to equal tilde evaluated at epsilon is equal to 0 plus epsilon ds tilde d epsilon evaluated at epsilon is equal to 0 plus epsilon squared over 2 factorial, which is just 2. And you'll notice this is what we just wrote down a minute ago as the first variation, right? We took our first, the Gateau derivative being this, evaluated at epsilon is equal to 0. And we note from last class that we defined the first variation as the difference between our perturbed function and our real function. And clearly, well, maybe not clearly, but this is our real function. When we have epsilon is equal to 0, we recover y, we recover y prime. We don't have any of that messy perturbation anymore. So the difference between these two is just going to simply be epsilon ds bar d epsilon 0 plus now you might be thinking to yourself, the first variation, we just talked about the Gateau derivative, and it doesn't look like it has this epsilon term out front. What's happening? Well, we're going to set that first variation equal to 0, and so that epsilon's going to be gone when we get to this point up here. Oops. Okay. So we can unpack this a little bit here using the chain rule. And we can write that, well, the total derivative, oops, let's see, ds tilde d epsilon is going to be equal to x1, x2, and the derivative of the Lagrangian with respect to the derivative of x, and dx d epsilon. I'll explain what I'm doing in 1 second. Just let me write this down. So let's investigate what all these terms are, what I'm talking about here. So for one thing, we don't vary x. So if we take the derivative of x with respect to epsilon, we get 0. This doesn't enter the equation at all. The derivative of y tilde with respect to epsilon is what?
Just the whatever
The fancy end.
error function is.
Yeah, the eta.
Yeah,
Exactly.
yeah.
So this is just eta. And this one is just what?
Eta prime.
Yeah, it's eta prime. What am I doing? Oh, I forgot some notation over here really quickly. So remember, what I'm asking you to do right now is calculate the Gateau derivative, which is to take this thing, set it equal to 0. Take the derivative of your action that's perturbed with respect to epsilon, evaluate that at epsilon is equal to 0, and set that entire thing equal to 0. If we've done that, and we've calculated the first variation. And the first variation gives us our equilibrium solutions. I'm going to pause here and repeat myself and then take some questions. So the first variation is equal to 0 tells us we're at an equilibrium point. That's what our goal is. We would like to extremize our function, find the equilibrium point, so we set the first variation equal to 0. First variation can be calculated by taking a derivative of our perturbed function with respect to epsilon, then evaluating that at epsilon is equal to 0. That's what this notation means here. We actually have an explicit form for our perturbed action. It's this thing. But we have to be careful when we start taking derivatives of that. And we use the chain rule to take the derivative of the kind of outer function with respect to the inner function, and then multiply that by the derivative of the inner function with respect to the variable that we're differentiating with. That's the chain rule, right? So if I come back over here and I say, okay, I need to evaluate the derivative of this quantity that's inside my integral with respect to epsilon. The way I do that is I take the derivative of my Lagrangian with respect to the function x, in this case here, and multiply that by the derivative of my function with respect to the independent variable, the variable that I'm differentiating with. And so I have dl dx times dx d epsilon, dl dy tilde times dy tilde d epsilon, dl dy tilde prime times dy tilde prime d epsilon. Now, we don't perturb the independent variable. You don't perturb the independent variable, that's just always the case. So this quantity is 0, so it disappears. We don't know anything about this because I haven't told you what L is. So how do you take the derivative of L with respect to Y? You don't. You just leave it as an unknown for now. But we do know that this derivative is equal to eta. And we do know that this derivative is equal to eta prime. And so this simplifies to something that we can work with a bit better. And this simplifies to the derivative of L with respect to Y times eta, which is that second term, plus the derivative of our Lagrangian with respect to Y prime.
Is that Y tilde?
Yep, Y tilde, thank you. Dx is equal to 0. Whenever you get to this point, no, alarms should be sounding in your head. What do we need to do now?
Chain rule. Or the.
Yeah, integration by parts. Yeah, exactly. So we have the alarm bell that should be going off in your head are, we know some things about eta. For instance, we know that the value of eta at 2 points, we know the value of eta at x1, we know the value of eta at x2. We don't know anything about the value of eta prime. And so we can't reduce this to anything simpler until we can eliminate this eta prime variable. Sorry, I meant to say we don't know anything about eta prime. I think I said we don't know anything about y prime. We don't know anything about eta prime, so we need to get rid of eta prime. The way we get rid of eta prime is by integrating by parts. So I'm going to pause for a second and ask you to integrate this quantity by parts. Take a second and try to work that out. Oh, are people doing okay? Either feel like you got it or you're ready for me to show you what the answer is. I forgot a step. Doesn't change any of the math you just did, but it does clarify probably one point of possible confusion, which is that the first thing we did here, I only did one of the two steps. So the first step I did was I took the derivative of this action with respect to epsilon. That's what the result of this is. And we were able to insert eta for these derivatives here and remove this term entirely. But the thing I forgot to do was I forgot to say, let's evaluate this at epsilon is equal to 0. So let's do that now. Let's use orange for that. So what happens when we evaluate this at epsilon is equal to 0? Well, what happens is, oh, I can't do that. What happens is y tilde at epsilon equals 0 becomes y. Y prime tilde at epsilon evaluated at 0 becomes y prime, right? These are the functions. Y is equal to y tilde is equal to y plus epsilon eta. So we take the derivative and then we set epsilon is exactly equal to 0. So we recover the variables that we want to be working with. And like I said, this doesn't do anything to change your math, except it's going to get rid of all those tildes, and we don't have to work in that perturbed space anymore. But evaluating this at epsilon is equal to 0 gives us the derivative of the Lagrangian with respect to y times eta plus the derivative of the Lagrangian with respect to y prime times eta prime dx is equal to 0. Now we can integrate by parts. Like I said, if you already did this, it won't change anything except getting rid of the tildes and your y's. If you didn't do this, let me show you what the integration by parts looks like. So we have this integral from x1 to x2 of the derivative of our Lagrangian with respect to y prime times eta prime dx. This is going to be equal to the derivative of our Lagrangian times y prime times eta evaluated at x1 and x2, minus the integral of x1 to x2 of d by dx of my derivative of the Lagrangian with respect to y prime, and that whole quantity is multiplied by eta. Do people get this? I'm seeing a couple nodding heads here online.
Do we take the derivative of dl of y prime?
You kind of can't, because it doesn't exactly have a meaning until we input something in for L. The question was, do we take the derivative of L? So we have that d by dx. Do we just leave it there? And the answer is you just kind of leave it there for now. Yep, question in here?
Is that a partial dx?
No,
Okay.
because we only have one independent variable.
Okay.
So we're taking the it's because of, I believe it's because of this that it reduces to an ordinary derivative. I believe it's because we're not varying that. So the Lagrangian depends on Lagrangian is an independent function of x and dependent function on y and y prime. And so when you take the derivatives of it with respect to y and y prime, those are partial derivatives. But I think I know that it's right. What I'm bumbling through is the explanation for it.
I asked because we did partial on little plus in there. The
The
partial.
Lagrangian, yeah.
But,
No, that's confusing. I'll try to. I'm trying to think about that. Okay. Let's do some thinking here. In this case, this is asking you to evaluate this at x1 and x2. This term is going to go away. Again, this is not always true. And in particular, and I think we'll show this probably not today, but maybe next class. In particular, you can actually learn a lot from this term here, because what this term represents are, you actually can derive the boundary conditions to your problem by using this variational method. And that's actually really powerful. It's one of those subtler things that I think will be lost at this point, and that's okay. But you actually derive not only the governing equations, but also some of the boundary conditions to your problem. And that's what this is. I mean, if you think about what that's saying, is it's saying like the condition on that term evaluated at 2 points, which are on the boundary of the curve that we're looking for. So you actually can get a part of your boundary conditions for free. Here, we won't go into that, but I will show that in a bit more detail later. But this term I highlighted in yellow vanishes. And so we can kind of put all this back together. This term stays the same here. Nothing has to happen here. So we just take this term and add to it this term. And what we arrive at is that the first variation in S, evaluated from x1 to x2, is going to look like the derivative of your Lagrangian with respect to y minus d by dx of the derivative of your Lagrangian with respect to y prime times eta dx. And the basic lemma of the calculus of variations is that since eta is arbitrary, the thing inside the square brackets has to vanish. If the integral of this quantity times something that's not 0 has to equal 0. Why does it have to equal 0? Because the first variation has to be 0 for this to be an extremum of the problem. And if this is not 0, then the only option is that this thing equals 0. Again, we did a lot of work to arrive at an equation that I think is probably familiar to you. What is this equation? Is this not familiar? I always think it's going to be familiar, but I guess it's maybe not. Would it look? Nope.
Is it to derive the equations of motion using Lagrangian mechanics?
Yeah, these are the Euler-Lagrange equations, which I would assume you've probably seen in dynamics. Any Lagrangian that can be written in the form with one independent variable, one dependent variable, and one derivative of that dependent variable. You can plug that into the Euler-Lagrange equations, and what you'll get out is a second order ordinary differential equation for the unknown function y of x. I thought this would be more exciting because I thought you had all seen this before, but apparently it's just a bunch of letters. But this is important. This is the basis for like the most simple dynamical systems. You have like a 1D problem. You have the Euler-Lagrange equations. You plug L in, and you arrive at the ordinary differential equation, second order, that you need to solve to describe, as was said a moment ago, the equations of motion for your system. If you are like kind of interested, but maybe also kind of not really sure if you know exactly what you're doing, then here's what you can do. Oops. When you have some spare time, test your ability and figure out the Euler-Lagrange equations when you have second derivatives appearing. This occurs whenever you're trying to deal with, for instance, the shape of a deflected beam. Well, you'll end up with second derivatives, because second derivatives talk about curvatures. And so this is useful. If you want to study the vibration of thin plates, your plate equations will have 4 derivatives in y. So you could write down the Euler-Lagrange equations for x, y, y prime, y double prime, y triple prime, y quadruple prime, and you go through the same process. What ends up happening is you get really good at integrating by parts, because what happens is you integrate by parts, and then you end up with going from eta double prime to eta prime, and then you integrate by parts again to get eta. You can do this when there are multiple independent variables. So you could do this when you have, for instance, a plate. You would need x and y, and you would have an out of plane deflection, which maybe would be like w. You'd have a spatial direction in one spatial component of one direction and another direction, and then deflection in the third. So you could do this when you are not dealing with partial derivatives, but you're dealing with Laplacians and biharmonics. The same approach works. Instead of And then you can, instead of integrating by parts, when you're dealing with things that have a Laplacian, you're looking at more utilizing Green's theorem. Again, this idea of kind of like figure out what's happening in the bulk, throw things to the edge. That's basically what we did here, right? This is what remains in the bulk, in between the points x1 and x2. And this is what's happening at the edge. And if you think about, you can like dig up what's happening when you learned about Stokes' theorem or divergence theorem, if you will. What you're doing is you're basically kind of taking a function that you're integrating over and separating it into stuff that's happening in the bulk, stuff that's happening on the boundary. If you can get that conceptual understanding, it can really be quite important, especially when you have problems that have, for instance, boundary layers, like you're working on with your midterm. If you have stuff with boundary layers, then what you can do is kind of see if you can write down the equations, separate things out into what's happening on the boundary, what's happening in the bulk, and solve these things kind of separately. I've done a lot of work in shell theory, and the equations of shell theory are just almost, in general, impossible to solve, except for very specific kind of scenarios. And one of the biggest things we did was kind of recognize that we could simplify our problem by working with a full sphere, like applying the divergence theorem many times, and throwing everything to the boundary, and there's no boundary on a complete sphere, and so you get to throw away a lot of terms, and then we were able to simplify things to solve for instance, when a thin shell that's growing would buckle and completely lose the shape that it started out with. The conceptual leap was harder than the mathematical leap, and part of me talking through these things about integration by parts, understanding like what you're kind of physically doing when you're applying these mathematics is to help you be able to make some of these conceptual leaps. So if you want to test your ability, try this thing out, see if you can derive it. I'll give you a hint, it's going to look a lot like this, but you're going to have second derivative terms added onto this. The benefit of the Euler-Lagrange equations are a lot of the times, you don't actually need to start with your function, perturb it, calculate the first variation. If you can just identify, hey, my functional looks like this, grab the right Euler-Lagrange equation, stick your functional into here, and then you have the equations that you need to solve. In just a minute, we'll do exactly that. Let's take a 5-minute break. Feel free to pepper me with questions, and then we'll solve the most basic and elementary problem of the calculus variations using the Euler-Lagrange equations.
I've got a quick question.
Yeah.
So going back to the step where you wrote out expand, and you got up to delta s equals s tilde minus s. So I get up to that, but then can you go over again how you got from that to the next step with the integral?
Sure. Yeah, great question. So you come back up to here. What we want to calculate is this, because this is our first variation. And if our first variation is equal to 0, then we have found the equilibrium point. We've found the minimizers to our problem. So we want to do this, which means we want to take the derivative of s with respect to epsilon, and then we want to evaluate that when epsilon is equal to 0. So to go over here, I said here's s tilde, is this quantity right here. So we need to take the derivative. Actually, I think I did it here. Yeah, I think I did it with y tildes. So let's start with this thing here. So I need you to take the derivative of s knowing that s tilde is the integral of the Lagrangian of x, y tilde prime, right? How do you do that? Well, you can't just, so I'm actually asking you to take the derivative of the stuff inside there. So I want you to do like d by d epsilon of this stuff. But you can't take the derivative of L because L is a function of X. L is a function of Y, which is a function of X. This gets to your question about why it's an ordinary derivative, because L is a function of X, Y, and Y prime, but Y is only a function of X, and X is not a function of anything. Y prime is a function of X. So, Jacob, to answer your question, we need to take the derivative of this awful looking thing, which is almost too vague to even know what to do with. But it's not that bad, because you need to take the derivative of L. So here's where we need to use the chain rule, because we don't have a function, we have a function of a function. So we need to take the derivative of L with respect to X, and then take the derivative of X with respect to epsilon. That's the basic idea of the chain rule. Take the derivative of the function, take the derivative of the functional with respect to the function times the derivative of the function with respect to the variable. So we need to take the derivative of L with respect to X times the derivative of X with respect to epsilon. That first term doesn't matter at all, goes away. We need to do that for all of them. We add them all up. This starts to look like the total derivative, if you will. So we come over here and we say, okay, we have to add to that the derivative of L with respect to Y tilde times the derivative of Y tilde with respect to epsilon. So it's just the chain rule, and you're just adding them up together. Does that help?
Yeah, that does. And so we're just not worrying about the epsilon squared term from the delta S?
The first variation is always this, oh gosh.
Oh, right.
And this would be the second. Let me do this a different way, actually. Sorry. This is the first variation. This is the second variation. The first variation tells us we found a stationary point. The second variation will tell us if it's a minimum or a maximum, if it's stable or unstable. So for the first variation, which is all that we're interested in, we only need to worry about the Gateau derivative, which is that ds by d epsilon, set epsilon equals 0. The fact that, so you can think of it a different way if you want. You could say, actually, I'm not comfortable throwing away this higher order term. But once you do that, you're going to be left with this term is going to be multiplied by epsilon. This term is going to be multiplied by epsilon squared. All of that term is going to be equal to 0. So you'll be able to kind of factor out an epsilon, so this thing will go away. This will be epsilon times the second variation, epsilon squared times the third variation, so on and so forth. When you set epsilon equal to 0, all these terms are going to go away. So you're only going to be concerned with this remaining quantity for the first variation. And so those are like two ways to say the same thing, I guess. This is the result of the chain rule. And then we replace epsilon with epsilon equal to 0. And we get down here. And then it's just integration by parts. Does that help?
Yeah, that makes sense. Thank you.
The first variation only ever concerns itself with order epsilon. Second variation concerns itself with order epsilon squared. Third variation, so on and so forth.
I have a question with the chain rule expansion and the integration over there. Why does the DL the D Lagrangian d eta sorry, the dl dy eta term between x2 and x1, why is that not included in the final ds equation?
Is it the term? Is it the term down here you're talking about?
It's the term that you get when you do the chain rule. Sorry, the integration, yeah, of the yellow one.
The yellow one?
Yeah.
Yeah, perfect. So think about what this term means. I'm gonna let me take this thing out here. Okay, so let's think about this term explicitly. I'm gonna write it out with some more cumbersome notation for clarity. Right?
Yeah.
Calculus. So if you recall what we said up here, eta at those terms is exactly equal to 0.
Oh, so the endpoints are the same.
The endpoints have to be the same.
Right.
Yep.
That makes sense. Thank you.
Yep. Other questions? Yeah, Reese.
I was just curious about the bonus fund
Yeah.
problem. So, yeah, essentially, I think I kind of get how to do it, but as you were saying, when you're dealing with the double prime, you do integration by parts, and essentially the eta double prime will become eta prime.
And a boundary term.
Yes.
Yep.
So when it's basically the thing we we're just talking about, when we're evaluating eta prime at x1 and x2, we don't really know what those values are, right? So like what?
Yeah, so this is a good question. So the question asked by Reese here was, if I wanted to try this problem out, what I'll end up with is boundary terms that say something like dl d, for instance, dy prime times eta prime is evaluated at x2 and x1. So I would expect a term very similar to my term that's boxed in pink here, except my eta is now eta prime, and I don't know anything about eta prime. This is where I was referring offhand in the lecture to, you get some boundary conditions for free, because that's a boundary condition. That says that we know something about the quote unquote slope, if you will. If it's easier to think about it as a slope, we know something about the slope at these two boundaries. And so if you're doing this for the beam equation, which I think we do at some point, let me just check. Yeah, if you're doing this for the beam equation, what you end up with is an equation that will result in the boundary conditions at two ends, and you might know one or two of them. You might say, and this kind of gets into, excuse me, this gets into, let me just, I don't want to say this wrong. Yeah, there we go. Yeah, so you'll end up with, in that pink box, an eta prime term, and then these correspond to the sum of the boundary conditions in your problem that you would solve alongside of the governing equation. Just remember what the point of these things is. And I'm going to go back to what I'm saying right here, which is the point of this is that if I insert L into my Euler-Lagrange equations, what I get are a second order differential equation for y of x. But what you also get are some of the boundary conditions that you use alongside of that ODE. You don't get all of them, and I'm blanking on whether it's the kinematic conditions or the like the Neumann or the Dirichlet. I have it. I'm just blanking on it right now. You get some of the boundary conditions on your problem, and they just drop out. You're right. You can't cancel it, but you can still do everything else. You can still say, I'm going to grab the bulk terms. That's my governing equation, and I'm going to write down my term that I have this unknown eta prime or eta double prime or whatever. Those are going to be my boundary conditions, and we will do an example without where it's explicit. But you're right. You can't just throw it out now. It has to stick around. But it's a boundary term, so it's a boundary condition on the governing equation. So the point I want to make is the purpose of these Euler-Lagrange equations is you stick your Lagrangian into them, and they spit out a second order ODE for the unknown dependent variable. And in some cases, they're going to spit out, well, actually, in all cases, they're going to spit out some of the boundary conditions you need to solve that ODE, which is one of the reasons why people love variational calculus. I mean, so you might have been sitting here last class being like, why did we sit through all of this? Did it write down F equals MA? The boundary conditions on, like, for instance, a sheet of paper that is, I have a, yeah, perfect. The boundary conditions on a sheet of paper that has free edges are really complicated, and they're not something you can just intuit and just write down like what the boundary conditions are. To find the boundary conditions on a problem like this, where you have like a plate that's supported and you have free edges everywhere, it's incredibly complicated. But they just drop right out of the Euler-Lagrange with this variational method. They just show up, and they look really messy. Like if you look at the boundary conditions for a free plate that's vibrating, I mean, this is one of the hallmark problems of elasticity. Like this started almost all of elasticity of thin structures came from trying to solve this exact problem. Like what happens when you have a vibrating plate? Because it's kind of a cool story. So like violin makers in like I think it's like 1800s, maybe 1700s, the way they would test to see if their violin that they're shaping is going to sound really good is they would place sand on it, and then they would take the bow and they would put their finger on some parts of the plate, and they would vibrate the plate with the bow, and then they would put two fingers down and they would vibrate the plate with the bow, and there'd be like salt or sand on top of it. And what happens is the plate would vibrate and make these crazy vibrations, because it's a plate, and it doesn't just vibrate like a string, it's going to have weird modes. And so what happens is the sand or salt settles in all the nodes. Depending on how you constrain it, you activate different kind of fundamental frequencies of that plate. And so you get different patterns of sand. These patterns were called Chladni patterns, and they're really complex and really beautiful. And it really bothered, I think, like the King Louis of France? It's one of the kings of France set this out as like a big open problem to like, why does this, what are these patterns? Where are they coming from? And so this set out like a bunch of mechanicians to try to find the patterns of these vibrating plates, which was how they were using them to build violins. The problem was solved by Sophie Germain. She submitted it, I think, once, and then it was kind of off, and she like revised it, and then resubmitted it, and it was right, but because of how sexist everything was at that time, they basically would not let her into the Royal Society, or they ignored her solution until, I'm pretty sure, Lagrange basically was like, look, this is the right solution, like this needs to be elevated. It's a hugely important problem. It basically started the theory of plates and shells. It was all about trying to understand the vibrations of violin like wood. And part of the challenge is the boundary conditions on that free plate are really awful. you can go to the Boston Museum of Science, well, when it's not a pandemic, and in the basement, they have a cloudy pattern thing. Actually, hell, we're on the internet. Let's load up cloudy patterns. Let's see what YouTube has for us.
We're putting together crew.
Men. This is gonna be lit.
That's a, they're not gonna hit it with a bow, they're just take it pull up. Salt is just sitting in the nose. So it's super cool. This problem is still really hard. Like I actually tried to set this up as like it'd be a fun project for us to be doing. And these equations are still awful to solve, that it would take too long for me to, to be able to get you to generate these patterns, but I'm still working on that. But this is the vibration of a 2D object. So it's gonna have your Lagrangian here is gonna be X and Y, or your independent variables, and you're gonna have your out of plane deflection. So that's going to be the first derivative of, let's say, you're going to have your out of plane deflection, which we say, let's call it W. You're going to need to know slopes, so it's going to be W prime. You're going to need to know curvatures, because your plate is bending, so it's going to be W double prime. And you can arrive at the governing plate equations. You actually need to go all the way up to fourth order. And you end up with a biharmonic, which is like the Laplacian of a Laplacian. But you end up with the governing equations and the boundary conditions that you can then not solve, because I'm not good enough yet. But, all right. Cool. Well, with that, I want to do one last thing, which is a significantly simpler thing to do. It's perhaps the most elementary problem in all the calculus variations, and it is the problem of planar geodesics. This is a very complicated way of saying straight lines. But we don't know it's a straight line. All we know is that a geodesic is going to be the shortest distance between 2 points. And we would like a way to be able to figure out what the shortest distance between 2 points is. On flat paper, it's obvious to all of us that the shortest distance between 2 points is a straight line. We start to get a little bit like maybe confused when we think about like airplane routes, when you like fly to England by going over the North Pole. But you realize that what's happening are your planes are flying along spherical geodesics. So what's the shortest distance between 2 points on a sphere? This problem, so the Nobel Prize in Physics this year was split. And on the theoretical side, it was won by Roger Penrose. And Roger Penrose was proving something about, basically proving the existence of black holes. The way he proved the existence of black holes, there's a cool PBS video online on like, I can try to link to it somewhere. The way he proves it is he evaluates the geodesics of light traveling in and around a black hole and shows that if you can get in, you can't get out. And the light has to follow these geodesics, and it does. And if light follows these geodesics, then it allows for the likelihood of a black hole existing. So the whole basis for kind of proving the existence of black holes is built on the idea of shortest distance between 2 points in a complicated geometry. So this seems like a toy problem, and I guess in a way it is, but in more complicated spaces, it's really A, not trivial, and B, really important to kind of, in that case, it was to prove the existence of something that for decades people were not sure even existed at all. So this is cool. So what's the distance, the shortest distance between 2 points on some arbitrary manifold? We'll do it in flat space, and we'll do it, and we'll say that we're going to have some point which exists at a comma alpha, and some other point that exists at b comma beta. This is just the x location A, x location, y location alpha, x location B, and y location beta of these 2 points that we've drawn out here. So sometimes they usually just start with the equation of the arc length, but I am not someone who remembers stuff like the equations of the arc length. So I do remember stuff like the distance between 2 points in general. And if I have something like x naught and x1 and y naught and y1, then I know that delta x is the difference between these two. Delta y is the distance between those two. And I remember something from the distance equation. We're going to come back to this. This is what's called the Euclidean distance. Oops. And we'll talk a lot about Euclidean distance in a few lectures, but this is not capital S, it's just like S. Is going to be, take the square of these distances here. So I can measure the distance between these points like this. And you probably remember actually seeing the distance equation written a little differently because you don't use s squared, you use the square root. And so you end up with this awful square root of delta x squared plus delta y squared. Oops. And what I'm going to do to make our math a little better is I'm just going to multiply delta y squared by 1, multiply it by delta x over delta x squared. And so that becomes equals 1 plus the square root. Sorry, 1 plus delta y delta x squared. Everything here by 1. On to the square root. Hold on a second, sorry. And that's all multiplied by delta x. And then if I take the limit of these deltas as they go into some infinitesimal distance, then I can calculate s as the integral from over 1 plus dy dx squared times dx. Cool. So that's the distance equation where we've kind of non-dimensionalized it by taking the slope squared. And that's the function we want to find the minimum of. That's the arc length, right? We want to say what's the minimum arc length between 2 points. And we've just found the arc length just by going from kind of basic stuff that we learned a long time ago. And so we can come over here and we can say, well, the thing we want to minimize is the distance between points A and B. of the square root of 1 plus, why did I do this? We'll do it differently. 1 plus y prime squared dx. And this is our Lagrangian. Our Lagrangian here depends on x, depends on y, depends on y prime. Actually, our Lagrangian is even simpler. Our Lagrangian actually just depends on x and y prime. We don't need to know that for now. It just allows us to skip a step, but we're not going to skip that step for the moment. So this is our Lagrangian. The fact that that Lagrangian is a function of x, y, and y prime means we can use the Euler-Lagrange equations we just wrote down. So we don't have to do anything. We don't have to do the Guiteau derivative. We don't have to perturb it. We just have to say, okay, well, I'm going to stick L into my Lagrangian. So what's the Euler-Lagrange equations? The Euler-Lagrange equations say that d by dx of this since our Lagrangian doesn't depend on y at all, we get to just cancel out that term. And then we just have to deal with this thing here. So we need to evaluate the derivative of our Lagrangian. I like to do this kind of piecewise. Let's look at this thing first. So we would say this is going to be y prime. I'm going kind of fast here, just because we don't have a ton of time left. And then I need to take the derivative of this. So I'll take d by dx of that quantity. This equals y double prime, over 1 plus y prime squared. And after we take the derivative with respect to x, we get kind of messy 3/2 here. Does anyone know what that equation is? It looks familiar. Think about what I just asked you to do. I asked you to take the derivative of, to see how the slope is varying along my curve. It's the curvature. This is the curvature. So physically, what is this saying about the shortest distance between two points on a flat manifold? The curvature has to be 0. Now, what you just said, what was just said in class, is that it's a straight line. That's not what this says. This is just saying the curvature needs to be 0. This gets, I only equivocate because it gets a little more complicated in different spaces. It's saying, or I guess let me put it a different way. A straight line on a different manifold will have its curvature be 0, but might not look straight. Like a great circle around the Earth doesn't think it's curved, but it's curved in a way that's curved from like the center of the Earth, but not if you're on the line. That's confusing. It's not helping. So this is the fact that our curvature has to be 0. If I look at this, I can pretty quickly see something. This is not obvious. This one wasn't obvious to me, but look at the denominator. There is absolutely no choice for y prime that I can use that'll make the denominator 0, right? It's something over 1 plus something squared. No negative value. There's nothing you can do to get rid of the denominator. So in order for this quantity to be 0, the numerator has to be 0. Does everyone see that? Because that's the leap we're going to make here. There's nothing you can choose for y prime that makes the denominator 0. So the only way for this thing to be 0 is if the numerator is 0.
Saying y prime is real.
Saying y prime is real. Yes, I'm saying it's real. Yeah, I actually left out the description that this is on a plane of r squared, like a real plane, so I didn't write that down, but yes, exactly. It has to be, assuming it's real. You're in a real space. Okay. So this, ooh, that's not really, I'll do that anyway. So we're left with just this simple expression, which we can then integrate twice to find that y is equal to, let's see, we used a and b, so let's go with cx plus d. That looks like a straight line. And if we want, we could apply our boundary conditions to the second order ODE. And we would find that c is equal to, I'm just going to go quickly through this because you know the answer. C is going to be equal to the difference between the y spots over the x locations. X is actually equal to x minus the x location, A, that first point, so kind of rescaling it. And then D, it's a shift in y, right? So the x is going to be shifted by the x component of A, and the y is going to be shifted by the y component of A, which is going to be alpha. And what does that mean? It means that y equals mx plus b, or in more gory detail, it's a straight line. Now, we actually didn't prove that this is the shortest distance between 2 points. It actually, in fact, we just proved that this is the extremal distance between 2 points. It could be the longest. We know that it's not. If we wanted to guarantee that it's a minimum, we can check the second variation. I went really fast, but we got to skip a lot of steps because we derived the Euler-Lagrange equations. Once we identified our functional, which is kind of the tricky part, like recognizing all of this stuff here. Once we identify that, I'll draw. Once we identify that, then it's just a matter of kind of looking at our functional, identifying the form of the Lagrangian, sticking it into the appropriate Lagrange equations, and minimizing, and you're good to go. Questions? All right. Well, see you on Thursday or in office hours. Thanks, everyone.